Let's continue our beautiful lesson in our beautiful university. Okay, so torque is equal to magnetic dipole moment cross product E. It matters if it's E cross P or P cross E. It matters, right? Because E cross P is negative of P cross E. You do know this, right? Good. So, for example, yes, you had a question. Where are you? Yes. Square. So we have a square, let's say. So a negative charge here, negative Q here, plus Q here. We usually don't ask this kind of complicated questions. This would be an example of quadrupole, I guess, not a dipole. So this is the question. So what do you want here?
I want to find the electric field in a point.
Yes, that's a separate issue. Finding electric field in a point is a different subject. So what I'm trying to say here with this electric field is that I'm applying electric field. This electric field comes from outside, and the dipole is interacting with that outside electric field. Does it make sense? So for this problem, like find the electric field somewhere here, let's say, that's a separate issue, right?
So we don't deal with it.
What do you mean?
Like finding the electric field with dipole and quadrupole.
It's not the subject of dipole part. It's the subject of the previous part, okay? But the subject of this part would be this. For example, let me give you an example. Let's find the electric field at this point. You might say, Hocam, how this is relevant? This is relevant because here we have a clear dipole moment pointing in this direction. And we are going to first find the electric field because of individual charges, and then we will rewrite that expression in terms of dipole moment. Okay? So, if this distance over here is r, let's call it r, this distance over here is r, from the center of the dipole to the point, then I can write that electric field is K plus Q over R plus L over 2 squared minus KQ over R minus L over 2. This should be minus, this should be plus. So the electric field due to this positive charge is larger than the electric field due to this negative charge because this one is closer, right? So this is an exact solution. This is the exact value of the electric field over there. But we can now make approximation. Let's find the electric field in the case when R is much larger than L. Okay. In that case, I can write E for R. I can rewrite E as KQ over R squared. And I'm going to write it like this. And you tell me if you like it or not. Do you understand this? Everybody gets it? Yes? So what do we do with this? What can we do with that? Yes.
Depending on what we want, we could apply binomial theorem or
Yes.
just say that since R is a lot bigger than L, this whole thing is like 1.
Yes, but if you do that, then this is 1, this is 1, 1 minus 1 is 0. We want something to remain, so we go with the binomial, right? So this is, the whole thing is 1 minus L over 2R to the power of minus 2, which means that if you do the approximation, it's 1 plus 2L over 2R, while this one is 1 minus 2L over 2R, right? What do you get when you do all this algebra? KQ over R squared. So ones cancel each other, and the rest is 2L over R, E. So it turns out that the electric field due to a dipole is 2KQL over R cubed when R is much larger than L. Right? Did you follow this? So you can see that there is a QL there. There's a QL, and QL can be replaced by P. So 2KP over R cubed. Okay, let me just highlight it with this. Do you have any question? Comments? Yes.
Would this apply even if the R and L was not in the same direction or axis, because R is sufficiently large enough?
So concerning the same, you mean axis?
Axis,
No.
right.
No, it wouldn't.
Be on the same axis as L for this.
Yes, that's a good thing that we can also solve. Do I want to solve it right now? Not so much.
In the syllabus, we stated that we would finish Gauss's law with this figure.
Yes,
We don't
yes.
have time.
Yes, thank you. Thank you. Yeah, so you are right, absolutely. So the thing is that with monopole, the electric field goes with 1 over R squared. With dipole, it goes like, as you can see, 1 over R cubed. Do you see it? And with quadrupole, we are expecting it to go with 1 over R to the 4. If you want, you can show that that is the case. Okay? Tell me.
Should we know the approximation of
Which one? What you should know. Let me just tell you what you should know, and the rest you shouldn't. The rest you should be able to derive if necessary. But what you should know is that dipole moment is Q times L, and you should know that it is defined for this particular system. Like, this is absolutely necessary to know, and this is absolutely necessary to know, the torque. That's it.
remember the bus formula?
No. No. No. But I mean, if you can remember, but no, just remember the important ones. Another thing that you should remember is energy, potential energy due to dipole moment. Potential energy due to dipole in E field. Let's say I have a dipole and it's inside an electric field. So let's say this is the electric field, and this is my dipole. What the dipole wants to do? Rotate. Which way?
In the same way as the electric field.
It wants to align with the electric field, right? And when something achieves what it wants to achieve, does its energy goes lower or higher? Lower, right? So that's why potential energy is defined. Potential energy is never vector. P dot E. Okay. I was going to make a point and I wrote exactly the opposite. Minus P dot E. Why? When it is aligned, it is as negative as possible, right? And when it is opposite, if you remember, when the vectors are opposite, it's as negative as it gets. Plus the negativity here, you are going to get positive. In other words, in other pictures, because I'm going to draw a picture now. This is U. This is U. And this is its values. Let me just shift it over here. And let's say this is theta. Okay, when you have 0 theta,
Unstable equilibrium.
Exactly.
Theta şeyden geliyor.
Can you give me a moment to think? Okay, let's do it step by step. So when it is 0 theta, what is the energy? It's minus PE, right? Are you following? So when P is perfectly aligned with E, E is like this, P is like this, then the energy is negative PE. Do you agree? So that corresponds to 0 theta. When it is pi over 2 theta, meaning that this is like this and the electric field is like this. What is the energy? 0, because that product brings cosine theta, right? Let me just write it down. U is equal to minus P magnitude times E magnitude times cosine theta. So cosine pi over 2 is 0. When it is plus P, then E and P are misaligned, so we have maximum energy. So we have something like this. It's very hard to draw. Okay? Is everyone happy with this? So for example, do you have any questions? Yes. Yes.
Şeyden bu
Yes, it is. It is because in that note I didn't write theta. I shifted it. As you can see in the note, that's why I was confused. I didn't put a value for the x-axis. It's just something. Okay? So in my notes, let me just in my notes it looks like this. And just to fix the confusion, let me tell you that for this one, this corresponds to 0, this corresponds to pi, this corresponds to 0 again, or 2 pi if you want. Or let's go in the negative direction. Doesn't matter, it's a cosine, it just repeats. Are you happy? Yes? Good. That's in the notes, so let me just shrink it. And write it down, 2020, 22 notes. Done. One chapter is gone. We start with Gauss now. Do you have any questions? So here's the thing. We started 10 minutes late because of air conditioning and stuff like that. Now, I will do 20 more minutes, 24 minutes of Gauss. Then we do 10 minutes of quiz. That does seem fair. Then we do 10 minutes of break. Then we do another 50 minutes of Gauss. Good? If you have time, we can extend the break if you need more air just to refresh. No. Because someone is saying no, that's why I'm saying no. Do you?
I think as soon as possible is better.
Okay. Okay. Okay. Do you regret shifting the hour to the last hour now?
Aslında bir önceki saat boş musun? İlk saat mesela. O da mantıklı. Sınıf boş.
İki yıl mı ya? 2 yıl mı?
Evet. 3'ten
Yine böyle yorulmuş olacaksınız bu saatte. Sadece daha serin olacak hava. Daha iyi değil mi? Öyle mi? Kaçta?
5:40'da.
Okay. If the class is empty, available, and if you agree, we can switch 1 hour early. Does anyone object that, first of all? No? So we start 1 hour early if the class is if the classroom is available. I will let you know. Hmm?
We came early and class was available.
Yes, that's right. That's right. So probably we will switch it like that. Sorry. For today, I'm sorry. Good. Gauss's law. We start new chapter. Imagine Gauss's law is a computer and the password to enter is symmetry, okay? Keep that always at the back of your head. Symmetry. Is this system symmetric? What kind of symmetry does it have, okay? We will come to the point, to this word over and over. But let's start, before going deep, let's start with a definition of electric flux. So, electric flux. Electric flux is something that is proportional to the number of field lines. So, imagine this charge, right? Plus Q. And it has some field lines running out. how many lines are crossed if we look at this surface? All of them. So 8, right? How many lines if you go here? Same. So electric flux is proportional to number of electric field lines. Right? And as you can see, since it's proportional, then the electric flux over here and over here will be the same. Okay, what is the definition of electric flux? Electric flux is defined as, let me just give you a definition that is given with an integral. Okay, so let's say you have a surface, you have a weird surface, right? And let me just make the surface a bit more look to the other side. Let's say the electric field comes in from here in this direction. This is the electric field. And it is a surface, right? So it is composed of all these different places on the surface. And you might choose a tiny bit of a surface over here, might be looking that way. Tiny bit of a surface over here might be looking down that way, right? So you basically take the dot product of all that. Okay? You take the dot product of all that and sum it up. Let me tell you this way. Electric flux is the total electric field times the area, the amount of area that is perpendicular to the electric field. So if the area is directly perpendicular, then all of it is included in the flux. But if the area is tilted, then the perpendicular part of the area is this. So it's less, right? Let me just give you this kind of. So this is the electric field. There is a surface over here that is directly perpendicular to this. Then the flux is just simply E times A. Because all of the area is perpendicular. Is this clear? Yes.
Why dA is vector?
Very good question. dA is vector because you want to know which way the area is pointing at. So maybe it is like this. So electric field is coming in, but dA is pointing this way. So dA is always pointing perpendicular to the surface. Okay? So dA is pointing perpendicular to the surface, and E comes in. And what happens in this particular case? In this particular case, E and A have angles. There's an angle between them, right? So we are going to get cosine of this angle. So I can write it like this as well. E times A times cosine theta. Is this clear? Any questions? No? For example, could be a semisphere like this. Okay? and it has the inner part as well, of course. Is this a nice, do you understand it? It's half of the sphere, empty. It's like catching butterflies kind of thing, yes? So let's say this is R, this is E. What is the total flux on this surface? So as you can see, some of the electric field will come like this, but the dA will point like this, right? But in some parts, the electric field will again be like that, but dA will point like this. The thing is that the area that is perfectly perpendicular is pi r squared. So even without taking that integral, you can simply write the flux to be E times pi r squared. Did you understand this one?
I'm confused.
So let me just put area here. So this area over here is pi r squared, right? That's the area that catches all the perpendicularly flying butterflies of electric field, right? It doesn't matter how the rest of the thing looks like.
It cannot be.
You see? The number of electric field, you can also think of it in terms of the number of electric field lines. The number of electric field, I'm assuming that all of them are entering perpendicularly like this. So let's say it catches 7 electric field lines, right? If this surface catches 7 perpendicularly coming electric field lines, then this surface will also catch 7. So it's the same amount. So the flux over here is pi r squared. Of course, you are going to ask me why we are bothering ourselves with this, because it will appear in Gauss's law and it will make our life quite easy. Tell me.
This is because electric field is uniform, right?
This is because electric field is uniform. Electric field might not be uniform. That's a problem. So, I happen to have an example for that as well. I will come to that example soon. There is another question? Yes.
So the electric field does not go outside of the surface.
It does. It penetrates through. Did I mislead you by saying that catching electric field, so that you thought that electric field would not go to the other side? I didn't mean to say that. But I mean like penetrating. Yes.
The area vector going to opposite side of the electric field vector. I mean, in order to formula because of the cross sign, isn't it become 0? I didn't understand.
Very good question. So the direction of the area vector, we actually have sort of freedom there to choose which way it directs, depending on our purpose. Okay. In this particular case, my purpose was to show you that the flux over here is the same as the flux over here. But if it's a closed surface, let's say it's a closed surface like this, okay, then usually we show the area vectors point outwards like a hedgehog, okay? And then the electric field lines, let's say this is uniform, let's say, okay? Then the total flux is 0, because these ones will produce the negative ones, as you mentioned, and these ones will produce the positive ones. So it will totally be 0. Any other questions? Yes.
It's not empty inside, right?
It is empty inside.
But then the area is not pi r squared. It's
Which, you mean this one?
yeah.
Yes, it is empty. For this one, I was thinking about this thing that you catch butterfly with.
It's empty inside.
Yes.
But then the
But we are thinking about surface anyways.
and surface is half of the 4 pi squared. It's
I think I'm confusing you with this. Right? Let me give you simple stuff, okay? Let me give you simple stuff. So here's a simple thing. Here's a simple, very simple thing. I have this plus q. I have this plus q. And I have an area over here. And the distance of that area is r1. Okay? My question is, how much electric flux do I have there? So what is the total electric flux that comes out of here, phi 1? Simple, right? Very understandable, right? Geometrically and whatnot. It's a spherical it's a spherical shell. Now, anyone who wants to answer this question? Yes?
Electric fields
Yes?
and 4 pi r squared.
Yes, very good. So phi 1 is going to be E1 times 4 pi R1 squared, right? So E times A directly. Why? Because all electric field lines are leaving perpendicularly. So you can simply write E times A. Did you follow this? Yes? But what is E1? E1 is 1 over 4 pi epsilon 0 times Q over R1 squared. Do you see there are going to be lots of cancellations? So phi 1 is Q over epsilon 0. Just as we expected, it comes out independent of R1. Why do we expect this? Because I told you that electric flux is proportional to number of field lines, and then I told you that the number of field lines crossing this surface and this surface are the same. So it should have the same flux. That's what we get. So for a spherical, for a point charge, this is the flux it creates. Now, do we understand even better why in the electric field lines case we drew the lines proportional to charge? Do you remember? If it was 2q, it would have double the number of lines because it has the double of the flux, because it's only proportional to charge. Any questions? Yes?
Actually, I was thinking the other side, all of the vectors can compensate them in order to symmetry.
Which vectors?
For example, this and the other side of the.
Oh, okay. Very good question. Very, very good question. So the thing is that dA over here points this way, but dA over here points that way. So dA and dE are always aligned in this case. So they always contribute a positive value to the total. Okay? Good. If I take the same surface, duplicate, oops, I couldn't duplicate. Let me duplicate. Remember, DEAs look like this, right? Like a hedgehog. If I apply an electric field like this from outside, then the flux is 0, because then this one will cancel this one will cancel this one will cancel this one. Then that will happen. But in this case, it's coming from inside. Okay? Very good. Coming back to the problem of non-uniform electric field, Efe? Non-uniform electric field. Let's do it. So let's say I have an electric field that looks like this. It's basically E0 over L times Y times I. I have such an electric field. What do you imagine when you see something like this?
It is in the x direction, and as we go up in the y direction, it increases.
Very good. So this is the y-axis, and when y is 0, the electric field is 0, but then it increases. Okay, it's larger here, larger here, larger here, larger here. Yes, everybody understands this? Now I put a surface. Let's say I put a surface over here. Okay, a square. So what is the flux? And this is y equals to 0, this is y equals to L. Do you understand the question? Yes? Everybody understands the question?
The square has an equal.
No, it doesn't. It's very hard to draw three-dimensional stuff in two dimensions, but no, it doesn't. So let me then actually tilt this one a little bit, maybe. So it's going in. I think I made it worse. But this is better, right? So it's going in. And at the bottom, it's less. For example, over here, it's this much. Over here, it's larger. Over here, it's even larger. So what do you need? You need an integral. So you are going to have y, let's say y, and then you are going to have dy over here. And the dA is going to be, you tell me, what is dy times L. Right? And the flux is going to be integral going from 0 to L E dA. It's always perpendicular, right? So what do I get? 0 to L E0 over L times y times L times dy, right? Tell me.
The upper index of the first integral cannot be L though.
Why not?
If it is the A, it should be A. The L square or L square. Get what I'm saying, right?
I don't get it. So I switched dA to L dy.
But in the first integral, upper index.
Oh, yeah.
It should be.
Yes. Very good. So as a result, this one goes away. E0 is integral of y dy. Do we encounter a new integral here? Not at all. This is what we have seen already. E0 times y squared evaluated at L and 0, y squared over 2. So you get E0 times L squared over 2. Do I match the units? Yes, I do. Because it should be Newton per Coulomb times meter squared. And what was the unit of flux? Did we have a particular unit for flux? A name? No, that's capacitance. Okay, no, we don't. So Newton over Coulomb times meter squared. Alrighty, let's have a quiz.
Why is it L times dy to dA? I couldn't specify.
Why?
Why is it L times dy to dA?
Okay. Because I want to know the area of this portion, right? So I have a thickness of dy and the length of L.